We now have a functional, agentic tool calling model that fits natively on the absolute cheapest tier of edge hardware. It's called Needle 2. The entire model ships as a single 14-megabyte binary, and it executes a full conversational session within a hard 28-megabyte RAM limit. But the metric that actually commands attention is the throughput. On a standard Raspberry Pi 5, this model decodes over 500 tokens per second. That tiny footprint sails upward to heavily constrained but high-end wearables. On current-generation VR devices like the Meta Quest 3S and Apple Vision Pro, that same 14-megabyte model clocks between 400 and 1,500 tokens per second. These speeds definitively close the debate over whether local agents can physically execute on battery-class silicon. They can. The question is no longer, can it run here? The question is, what mathematical sacrifices were required to achieve this extreme level of compression? Needle 2 operates at a 5.4-point accuracy deficit compared to larger baseline models. You pay that accuracy cost to gain a massive efficiency benefit, a reported 2.3 times reduction in per-token compute compared to a standard dense transformer. The developers at Cactus Compute state this compute reduction is driven by their novel architecture, which they call the Simple Attention Network. But when auditing a release like this, we have to distinguish genuine architectural breakthroughs from clever parameter framing. Our goal today is to determine whether dropping 5.4 points in accuracy is a fair price for a 14-megabyte footprint, and whether the published data actually proves what caused that deficit in the first place. When building for battery-class hardware, there is one absolute imperative. You have to buy capability without buying memory bandwidth. Moving a byte out of flash costs orders of magnitude more energy than simple arithmetic. This is the Simple Attention Network. It is a 27-layer, 512-wide architecture built specifically to minimize arithmetic complexity. The first major swap occurs in the feed-forward layers. They replace standard learned dense projection matrices with fixed Walsh-Hadamard transforms. By swapping learned weights for pure mathematical structure, they drastically cut down the number of parameters the processor has to read from memory every single turn. The second mechanism relies on what they call engram memory tables. Instead of storing world knowledge inside the floating point operations of the main neural network stack, these engrams hold data in hashed lookup tables, trading complex flops for simple, low-cost memory reads. The third mechanism restricts the KV cache with a strict 256-token sliding window. By capping the context window, the engine guarantees a strict 28-megabyte RAM ceiling, regardless of how long the conversational session runs. Every single element of this architecture exists for one reason: to starve the processor of memory reads and save power at the edge. But structural efficiency alone doesn't get you down to 14 megabytes. To hit that footprint, the model's precision has to be gutted to CQ2-bit. Standard industry practice is to quantize models to 2-bit after the training process is complete. In small models, this post-training compression notoriously causes them to collapse and emit pure garbage. Cactus Compute avoids this by baking the CQ2-bit quantization into the model end-to-end, beginning on day 1 of pre-training. Because the compression is native, the weights never decompress into RAM. They expand directly inside vector registers, keeping the arithmetic path strictly end-8 from end to end. It proves that on highly constrained hardware, deployment precision cannot be an afterthought. It must dictate how the model is trained from the very beginning. Now, let's carefully audit their headline efficiency claim of a 2.3 times reduction in compute. If you want immediate technical teardowns of machine learning white papers the moment they drop, make sure you subscribe to the channel right now. Here is a standard transformer compute budget. This chart shows a dense transformer requiring 164 million floating point operations, or MFLOPs, per token. That 164 MFLOPs represents a dense network built with the exact same width and depth as Needle 2. But there's a sleight of hand here. Needle 2 has far fewer parameters than a dense transformer of that identical shape. If we look at a matched parameter transformer, we see that a standard model squeezed down to Needle's actual parameter count already operates at a much lower 87 MFLOPs per token. Needle 2 actually lands at 70 MFLOPs. This means the architecture's genuine mathematical innovation accounts for roughly a 20% efficiency gain, dropping from 87 down to 70. The rest of that 2.3 times headline is just parameter framing. This release features a rare trait for an AI launch. The developers explicitly admit in their own documentation that Needle 2 loses both of its headline benchmarks to its cited baselines. This table shows the mobile actions benchmark. Needle 2 scores a 63.7, while the larger LFM 2.5 230 million parameter model scores a 69.1. Here is the Berkeley function calling leaderboard, version 4, single-turn test. Needle 2 scores 42.6 against Function Gemma's 46.1. The developers attribute this to precision constraints. The baseline models are running at full F16 precision, while Needle is trapped at its highly compressed native CQ2 bit rate. They also acknowledge that the evaluation scope actually favors their model. Needle was trained strictly for agentic tool calling, whereas the baselines are general-purpose models carrying chat and prose. This level of raw transparency provides excellent context. However, it only gives us the price of the total bundle, without actually itemizing the costs of its internal components. What is missing from the data is a proper ablation study separating the impact of precision from the impact of parameter count. Because there is no F16 trained version of Needle and no CQ2-bit version of the baseline models, these two variables remain permanently tangled. We simply cannot mathematically decompose that 5.4-point accuracy gap. We don't know how much of the failure comes from having only 45 million parameters to work with, and how much comes from crushing those parameters down into 2 bits. Without this specific ablation, engineers watching this release don't know whether this new architecture or this specific quantization scheme is the actual right piece to copy for their own edge deployments. Finally, we have to drop to the absolute bottom rung of the hardware claims, the assertion that this runs on an ESP32S3 microcontroller. Right now, this capability is just a RAM fit claim. There is absolutely no measured MCU tokens per second throughput anywhere in their release documentation. Contrast that with our prior coverage of a 28.9 million parameter hobby model, which successfully measured and published 9.5 tokens per second on this exact same microchip. It highlights a real friction point. An unfunded hobby project published actual on-chip speeds, while this heavily funded product release has not yet met that standard. Until the actual microcontroller throughput numbers land, that 5.4-point accuracy deficit remains simply the known, non-negotiable price of hitting a 70 megaflop budget.